our next speaker is Masamichi Miyaji, who is from UC Berkeley. And he will talk to us about pseudo entropy, entanglement wedge, and cosmological islands.
Thanks for the introduction. So today I'd like to talk about my recent work and also the ongoing work with Jeff Pennington. So recently in the gravity community, we have had a very significant progress about our understanding of black holes. So now we know how to compute the entanglement entropy of Hawking radiation. And we confirmed that the page curve, the unitary page curve, can be reproduced from the gravitational path integral. And the formula for this entropy of radiation is the Island formula, and which is based on the so-called replica wormhole configuration of semi-classical gravity. The essence of this Island formula, one of the essence of the Island formula is that it captures the finiteness of the Hilbert's fifth dimension of gravity theory. And this finiteness of gravity theory Hilbert space is manifested in the so-called entropy bound, or the holographic entropy bound. So this bound says that if you consider the subregion in the space-time A.
Sorry, you're also muted.
Oh, sorry. So sorry to this online participants. Can you hear me now? Okay. So this bound says that if you consider the subregion A in the gravitational spacetime, and the entropy inside this subregion is bounded by the boundary area of the subregion. This bound follows from the covariant bound in the case of there's no singularities. So in my talk, I consider this entanglement entropy of a subregion in the presence of some initial singularity. And we will show that this similar bound as an entropy bound will follow from the one generalization of the Island formula. The difference from usual Island formula is that this Island formula uses the so-called pseudo entropy, which I will explain later. And this pseudo entropy naturally introduces pseudo entanglement wedge, which is a generalization of entanglement wedge.
I have a naive question.
Yes.
Does the number of singularities matter here?
So, I mean, once you have a singularity in moving a light sheet to the space-like slice, you can't apply the covariant bound.
No, I mean maybe I have more than one singularity.
Mm-hmm.
Will the same relation of your pseudo entropy still hold?
I haven't considered more than one singularity, only one singularity in the past. So this is the content of my talk. So I will start by reviewing the entanglement and the Island formula. And in the second part, I will explain what is the pseudo entropy and what's the pseudo entanglement. And in the third part, I will apply this pseudo entanglement to the understanding the entropy of gravitational prepared state. So let me start by reviewing what's entanglement and islands. So we know that in ADS-CFT, if you consider subregion A in the boundary, the entropy of A is computed by the area of Rutherford surface, which is the extremal surface in the ADS spacetime. And if you consider a subregion in the bulk, which is bounded by the RT surface and the subregion A, which this subregion is called the entanglement wedge. And this subregion has a very significant, it plays a significant role in this CFT because you could think of it as a gravity dual, in a sense, gravity dual of the subregion A in the boundary in the following sense. So if you consider the excitation in this bulk region, entanglement wedge, you can reconstruct this such excitation from the CFT state which lives in the boundary. So this is called the entanglement wedge reconstruction. More precisely, consider the following. So consider a map from the bulk state to the boundary state, so which is denoted by curly n. And we ask what's the map that recovers from boundary CFT state to the bulk excitation. That's a recovery map. So the existence of such recovery map is non-trivial. But in the gravity case, fortunately, this is guaranteed by the so-called JLMS formula. So JLMS formula says that the relative entropy between bulk states and boundary states are approximately equal at leading order in large N expansion. So if the equality is an exact equality, it is known that the PETS map is an exact recovery map, so that you can recover the bulk excitation or bulk states from the boundary CFT state. And this entanglement reconstruction plays an important role also in the Island formula. But let me just explain briefly that's what Island formula does. So in the Island formula, so when consider the black hole after page time, so the evaporating black hole after page time. So naively, the entanglement entropy of reservoir, which collect the Hawking radiation, seems to have too much entanglement entropy. So it seems like the entropy of the reservoir exceeds the degrees of freedom which should live in the black hole. So it looks like the evaporation process violates the quantum mechanics, unitarity of quantum mechanics. So in particular, the entropy of subregion A exceeds the area of black hole horizon, so especially violating the entropy bound. But because of the non-perturbative effect of gravity, you have a new geometric object inside the black hole horizon called the Entanglement Island, which modifies the rule for the entanglement entropy. So what it does is, because of the matter entropy, which contains the island region as well as the original subregion A, due to this entanglement entropy, the introduction of island reduces the entanglement entropy a lot, and essentially replaces by the area of the entanglement island. And the nice thing is that this entanglement island is in the entanglement wedge of the reservoir. So if you consider excitation in the reservoir, and so if you prepare the diary in the reservoir and throw in that diary into the black hole, so when this diary gets into the entanglement island, because the entanglement island is in the entanglement wedge, you can reconstruct this diary from the reservoir state by the very complicated manipulation and recover back the original diary. So this is a manifestation of the Haydn-Preskill protocol in terms of Entanglement Island. So this is an introduction. Is there any questions so far? If not, let me go on to what's a pseudo entropy and what's a pseudo entanglement wedge. So pseudo entropy is a kind of very new quantity which was introduced last year. This quantity is a von Neumann entropy for general transition metrics. So usually, when you consider the von Neumann entropy, the x is a state. So it's a Hermitian, is a positive, and has a unit trace. But in the pseudo entropy, although this has the same formula expression, x may be non-Hermitian, nor may have a complex eigenvalues, and so on. Once you consider the Jordan canonical form, you can write down the very familiar expression in terms of eigenvalues. But these eigenvalues is now not necessarily positive quantity. It could be negative or complex. Or
Masamichi?
Yes?
How do you define the logarithm?
So you have to make the Jordan canonical form so that you can define the matrix function in that way. That's how you define the logarithm and the matrix function. So it's defining matrix function is not necessarily unique, but in this case you can.
But when you have, for example, the expression on the right, if you want to take the logarithm of a negative number, do you need to choose some branch to define this pseudo entropy?
Right, that's true, yes.
Okay.
The nice thing about this pseudo entropy is that you can use usual replica trick to compute the pseudo entropy, as in the usual entanglement entropy. And more nicely, you can have a gravitational expression similar to the RT formula. So consider a spacetime due to this amplitude phi psi, and let's consider a transition matrix by tracing out the complement of subregion A. And you can define the pseudo entropy for the corresponding transition matrix. And by using the usual Lukowitz-Malassien argument, you can obtain that the extreme of surface in the bulk, which is dual to phi psi state. So the extremal surface, the area of the extremal surface in the bulk, compute the pseudo entropy. Yes.
Could you use psi or phi r in the picture? I'm confused about psi r.
Also, so for example, let's consider the Euclidean gravity, and you have the boundary is not necessarily time reflection symmetric. So you have a different excitation in the far past and the far future. So you evolve these two states into the middle and consider the pseudo entropy on that time subregion. And the gravity dual of this, the amplitude. So if you consider this pseudo entropy, then the extremal surface go inside this space-time dual to the overlap between the two different states. Does that make sense to you?
So sorry, naively, the pseudo entropy can it be complex valued?
Can be complex valued, but if you're only interested in the Euclidean gravity, then it's always real.
May I ask if looking from a per information theory perspective, what meaning does pseudo entropy have? Because the usual von Neumann entropy, it has a lot of good interpretations.
Yeah, that's a very good question, but I don't have an answer to it. It's not known. It's at the moment it's just some quantity which can be easily computed and has a similar property as a usual entanglement entropy. Also, it doesn't. Well, it's kind of obvious that this doesn't satisfy like strong subactivity, so on. Since it could be complex and so on.
Sorry, to follow up to John's question, so I mean, do you have to make sure that you choose the right branch cuts to get this answer, or do the branch cuts or natural chosen by the replica tree?
Oh, so you mean in the gravity case? So in the gravity case, it's only considered in the Euclidean case, so that the pseudo entropy is always real. So if you have a more general transition matrix which has a complex eigenvalue, you need to choose correct branch cut.
So kind of claim in a case that you have gravity dual, pseudo entropy is always good.
I mean, in this case, in more general case, you have to use the Schwinger-Keldysh to include the Lorentzian time evolution. And in that case, the question which raised by John and Sefer arises, I guess, I think. Choosing a branch.
It might be fair to say that the replica trick itself chooses a branch for you, because when you take the powers of the traces of the density matrix, those are all going to be real. At least in this case, they're all going to be real.
When the bulk is the Euclidean, yes.
Right.
That's true.
So if the pseudo entropy with where X is a transition matrix doesn't have an obvious information theoretic meaning, what is the reason for preferring it over, say, a Renyi pseudo entropy?
So you mean?
So I mean, if X was a probability distribution, then you would prefer the von Neumann entropy over the Renyi entropy because the von Neumann entropy has a more obvious information theoretic meaning.
Right.
But if X is not a probability distribution, why do you prefer the pseudo entropy with a log to the Renyi pseudo entropy?
Okay. Yeah. And from the perspective of gravity, it can be represented by the area of extreme surface. That's kind of an answer for gravity, but I don't have a information theoretic justification to prefer.
That was sort of the question. So the Renyi entropy does not have an obvious relation to the extremal surface.
No, you have to think about like the cosmic plane and so on. So it's include the back reactions and much more high non-trivial. Yes.
Can you explain a little bit more what you mean by the space-time dual, the dissonant product? In particular, are you imagining that phi and psi correspond to different geometry?
So yes. So the obvious example is like if you consider the disk and consider the time slice, which is consider some of the Euclidean sphere, and consider some circle which is not time reference symmetric. So in that case, the states prepared by the gravity dual for each state are different.
Yeah.
That's example. And in that case, you can't, so the extremal surface anchored from that such non-time reference symmetric slice is not, doesn't have an interpretation in terms of RT surface, in terms of entanglement entropy.
Right. What I'm trying to understand is that you do seem to invoke a particular unique geometry in which the area in which an extremal surface is being found.
Mm-hmm.
How do I construct?
Could I make a comment that might help?
Yeah.
The phi and psi are two boundary path integral preparations of states. And when you take your overlap, that gives you some boundary, surface over which some boundary conditions over which you can solve for bulk saddles. Right? So when you look at this overlap, it's going to be some boundary conditions for the gravitational path integral. And if you assume that there is some leading saddle, that's, I think, going to be the space-time that Masamichi is looking for an extremal surface in.
It's not always Euclidean?
Sorry?
Is the bulk always Euclidean?
You don't have to.
You don't have to?
So if when you want to concept real-time evolution, you have to use a Schwinger calculation.
Prepare
Yeah,
these states.
and agree it.
The circle, and then you go by Lorentzian. You can think of.
Yeah.
I'm still confused, I guess. So if I prepare some state on the CFT by some operator insertions on a circle, let's say, with one state, I know how to fill in using I can compute some gravitational path integral, which presumably is going to be dominated by some geometry. And with two states, what is it that I...
Well, the overlap is just some boundary path integral. You take two different preparations and then you sew them together. Right? You have like the vacuum, which is prepared by like the lower half of the sphere, and you have some other state, which is the lower half of the sphere plus an operator insertion.
Right.
And then you sew those together and you get some boundary thing, and that gives you boundary conditions for the gravitational path integral.
Thanks, John.
If I follow this protocol, then I get a number.
Mm-hmm.
Well, it always corresponds to some pseudo entropy of some matrix X, or it's possible that through this construction there will be a value that's not necessarily corresponding to this matrix and the pseudo entropy corresponding to it. Probably I can just randomly generate a matrix and then calculate the same quantity,
Mm-hmm.
and it still corresponds to like the thing you constructed.
So you considering the gravity drill, or?
Let's say I follow what John said and
Mm-hmm.
I made this prescription, and then I calculate the area of the extremal surface,
Mm-hmm.
and I get a number.
Okay.
But it's possible that I can just randomly find a matrix and calculate the same value, and it happens to correspond that number as well. So
Mm-hmm.
it probably doesn't really reflect the nature of pseudo entropy. Like, how can I prove that they have like a one-to-one correspondence somehow?
So
Like, does your X, that matrix, has
Mm-hmm.
like a strong connection with your phi and psi?
So you mean this transition matrix? Okay, I'm not sure I'm understanding your question correctly, but if you pick up any subregion randomly from the boundary, then it's likely to be that it defines a transition matrix instead of usual states. So that corresponds to the pseudo entropy in that case. Let me.
Does it matter if psi and phi are orthogonal or not?
When psi and psi are orthogonal, let's see. Yeah, I don't quite know, but that's a singular point since it's
So basically you want to assume that they're not.
right. Yeah, it's more non-trivial. Okay, so once we have the extreme surface in the bulk, and the boundary subregion. So it is very natural to think about what's the subregion bounded, the bulk subregion bounded by the RT surface for pseudo entropy and the boundary subregion. So this subregion we call the pseudo entanglement wedge for good reasons. So on this, the bulk subregion, pseudo entanglement wedge, you can also define a bulk transition matrix by tracing out the complement of the subregion by the following formula. So you can still discuss there's a correspondence between bulk transition matrix and the boundary transition matrix. So in that case, we are still, this is still ongoing about how to construct a Petz reconstruction map. But basically our strategy is to use a singular value decomposition and making use of the usual Petz map for the states. And let me work out some explicit example of pseudo entropy using the end of the world brane model. So the end of the world brane model, or West Coast model, is a simple model of gravity which coupled with the reservoir. And the important thing is that because of the finiteness of gravity Hilbert space, the inner product between different end of the world branes or the bulk states are not necessarily orthogonal. So this Rij has a non-trivial component. So we consider calculating the bulk pseudo entropy of the following transition matrix, so which is defined by the usual maximal entangled state, and it is deformation by matrix S. So this is not necessarily a state, and in general, it's a transition matrix. And by using the replica trick, we can find, as in the usual island story, there are two saddles. We can find there are two saddles for the replica partition function. So the one is the Hawking saddle, on which all the boundaries are disconnected. And in that case, the Rij is simply neglected. The other saddle, which is more interesting, is a replica wormhole saddle, where all the end of the world brane are connected. All the boundaries are connected via end of the world branes. So in this case, the Rij is important. And we can compute the pseudo entropy for these two saddles. And the result is in the Hawking saddle, it just gives the pseudo entropy or the matrix S. So it's in general, it can be complex. And on the other hand, in the replica wormhole saddle, the pseudo entropy is just a black hole entropy or just a topological part of the action. So the saddle which is actually realized is determined by the real part of the pseudo entropy. So when the real part of this pseudo entropy is smaller than S0, then Hawking saddle is realized, and the vice versa. So you may notice that there's a jump in the complex part of the pseudo entropy, since this part can be complex, but this is always real. So in my final part, I'd like to explain the application of the pseudo entanglement wedge and pseudo entropy to the entropy of gravitationally prepared state. So what I'll be interested in is the gravitationally prepared state. So this is a matter state which is prepared by gravity. So I have a gravitating spacetime, and we have a time slice in the future on which we turn off the gravity. So after the future time slice f, we don't have a gravity. And what I will be interested is the entanglement entropy on this future time slice. So in this case, we consider there's some initial conditions and the initial matter state on the past time slice, and which we take as regularized boundary states. So this is one generalization of the Hartle-Hawking prescription. So in the Hartle-Hawking, you don't have a past boundary, but it is smoothly capped off by the sphere.
Is this space-time Lorentzian?
We can make it Lorentzian, but
you're working in Euclidean for now?
Yes. So
think of gravity being switched up just below F, or I mean, is there some sense in which F is already
just below F, yeah. So this regularized boundary set has several nice properties. So the regularized boundary set defined by the conformally boundary states with a regularization. So this state is a pure state, but it's from local probes, it's thermal. So if you consider a small interval and compute the entanglement entropy, it obeys the volume law. It gives a thermal entropy. And this state is IR modification of the vacuum state. So at UV, it's the same as the vacuum state. And another thing is that entanglement entropy of very large subregion is given by the boundary entropy. And this state is usually used as a model for the global quench. So the change in the Hamiltonian globally at some instance suddenly. The explicit model I consider is the Euclidean JT gravity plus conformal matter plus end of the world brane on the initial time slice. And the result is as follows. For small subsystem, the entanglement entropy obeys the volume law. So naively, if you consider a very large subregion, it may violate. One would expect that it violates the entropy bound. So since it grows infinitely large. However, it is not the case. So when you consider the very large subsystems, there are two phases that dominate. The one is the boundary entry phase, so that entropy is given by the boundary entropy. Or there's an island phase where the entropy is given by the island, which appear in the past gravitating spacetime. Let me look at more closely at the island phase. So in island phase, there are various possible configuration which may contribute to the entropy, but once you take a look closer, there are only two dominant saddles that contribute to the entanglement entropy. So these are the two contributions. The one is where the island appears in the ket part of the geometry. The another one is island appearing in the broad part of the geometry. And each contribution gives rise to the pseudo entropy. Since this the entropy, the island configuration is not time reflection symmetric. And as a result, entanglement entropy is given by the average of two pseudo entropies, which is guaranteed to be real, since these two configurations are complex conjugated with each other. So the entropy is essentially given by the area of the entanglement island. Oh, sorry. Yeah, I'll finish soon. So we have reached that since the smallest entanglement entropy is always realized, we always have this inequality. So the entanglement entropy of the gravitational prepared state is always smaller than the area term from the entanglement island. And I note that this using the island rule is you have to impose some conditions on the initial state. The condition required by strong subadditivity is that the initial state should be sufficiently complicated. So if you consider some small subsystem which is decoupled, so if you assume that CFT has a small decoupled degrees of freedom, then this decoupled degrees of freedom should be maximally mixed with the rest of the system. So it must be very complicated state in order to be consistent with strong subadditivity. Let's skip that. Let's see. So let's see. Yeah. Okay. In the island phase, the pseudo entanglement reconstruction takes the following form. So this is a geometry for the wave function. And this shows that the entanglement island in the ket part of the geometry. And in the pseudo entanglement, what you consider is the transition matrix on the island plus the subregion A should be reconstructed in terms of fine-grained state on the final time slice on which the gravity is turned off. So let me summarize and give some comments. So we have considered a pseudo entanglement wedge, and it is replica one for pseudo entropy. And we have seen that the island version of the area bounds is always satisfied for gravitational prepared state, even in the presence of the initial singularity. So I didn't explain, but we also provided ADSP shift model for this configuration. And using the island route requires the initial state to be sufficiently complicated. The question is what's the Lorentzian generalization? In particular, since the island is located in the path gravity spacetime, so it is non-trivial to be consistent with the causality. Thanks for listening.
More questions?
For general X, is this actually bounded? Can it diverge?
Bounded from?
Like entropy is bounded by log of Hilbert space dimension.
Mm-hmm,
is this bounded or is it?
It should. Well, the absolute value should be bounded. Let's see. Yeah, I don't. Yeah, forget about it. Yeah. Mm-hmm. Yeah, that's true. Yeah. Yeah, I don't have an answer to that question. Thanks for asking.
Well, I think I figured out how to talk about this, at least in my own head, but I want to make sure.
Mm-hmm.
Maybe it'll be helpful. So you imagine you could, create a space-time, let's say, out of the vacuum, and that's psi.
Mm-hmm.
And you have another space-time that you've created out of some operator insertion, and that's phi.
Mm-hmm.
And you can create this second space-time out of the first one by applying some really complicated CFT operator.
Mm-hmm. Mm-hmm.
And that will convert this state into that state. And it looks like what you're trying to do here is to compute the entanglement entropy of that operator, the operator entanglement, and to figure out, in particular, where in the bulk this operator has support. Is that the right way to think about it? The operator I'm talking about, this x, is an operator that takes this sides at phi.
Mm-hmm.
It's a little weird because these states are not orthogonal.
Okay.
So ket psi bra phi does not. I mean, I guess it does take phi to psi. Just does.
Yeah, I see. You want to like have an orthogonal basis and then have an operator written in this orthogonal basis. And have it, I guess what I want to say is somehow I want to think of phi as being equal to x psi, and then therefore we're really only acting in the space-time defined by psi. And so there's not two different space-times, there's just one. And all we're asking about is where does this, now we insert this operator on the CFT.
Mm-hmm.
What is the nature of that operator and where does it have support in this bulk? I don't know, is that correct or not?
Yeah. Yeah. Let's talk about it later.
Okay.
I guess maybe I'm confused about similar issues, but when psi and phi
Mm-hmm.
are not orthogonal, are we assuming that psi and phi? So then we're presumably not assuming that psi and phi separately have each have a single gravity dual. In other words, if they did, right, if
Mm-hmm.
phi had a different bulk dual than
Mm-hmm.
phi, then they would be orthogonal to very good approximation.
Mm-hmm.
So at least one of these states somehow doesn't. I mean, I should be able to write one of these states like phi should be equal to psi plus something that gets projected out when you take this one product. I'm trying to understand how this extremal surface is related to those extremal surfaces that would appear in the individual.
Mm-hmm. Oh yeah. So that's I think that's a very non-trivial relation. So you can't. So for example, you have a different space-time, and consider it is possible to group by choosing the correct Cauchy slice for each geometry. But in that case, the entanglement entropy for each bulk space-time may not be the equivalent to the RT surface for the pseudo entropy. So it could lie on the different slice in general.
I guess we are
Yeah.
a little late, so we should. Yeah.
Let's thank the speaker again.